This lesson is going to have a few different purposes. One purpose will be to define and describe the ideas of shielding and nuclear charge as they relate to atoms of elements. The second purpose will be to take a look at what things they affect related to the behavior of atoms or elements. The important factor to consider is that these are highly related to what we know as valence electrons, known as the outermost electrons found on an atom. These electrons are the important ones because they're the ones involved in chemical bonding. They also describe the stability of an atom or how reactive an atom might be. If we recall, the metallic atoms have a tendency to want to lose or give away their valence electrons to become more stable. In general, our metallic elements are to the left of the zigzag line or the staircase. Counter to that, the nonmetal elements, excluding the noble gases, would tend to attract valence electrons to become more stable. We exclude the noble gases because of their stability in terms of what is known as octet, a pattern of stable condition of 8 valence electrons surrounding an atom. We'll look specifically at how ionization energy, atomic radius, electronegativity, and electron affinity are affected by the concepts of shielding and nuclear charge for atoms of elements. Let's begin by trying to describe what shielding and nuclear charge actually are. In order to understand it, it might be best to compare atoms of similarity in terms of metals compared to other metals, or nonmetals compared to other nonmetals. Therefore, we'll take a look at the atoms of lithium, sodium, and potassium, circled in red, and fluorine, chlorine, and bromine, circled in green. Notice that lithium, sodium, and potassium are all found in the same group. Therefore, they have the same number of valence electrons, or 1 valence electron. Likewise, fluorine, chlorine, and bromine are also found in the same group, with the same number of valence electrons, 7 valence electrons. The group, once again, can describe the number of valence electrons for the elements that are not considered the transition metals. Sometimes we can just look to see if they're in an A group, and that sometimes helps us identify that easier. Notice also when comparing that lithium and fluorine are actually found in the same period. Each are found in period number 2. This means that these atoms would have 2 energy levels occupied by electrons. If we were to compare sodium to chlorine, these are found in period 3, meaning there would now be 3 energy levels occupied by electrons. As we move down in period, we add energy levels occupied by electrons. Let's now take a look at what this might visually look like with something known as a Bohr model. Bohr models for each of the atoms of interest are shown: lithium, sodium, potassium, fluorine, chlorine, and bromine. Let's first describe what we mean by shielding. When looking at the illustration, this describes the elements of lithium and fluorine having the same shielding. Likewise, sodium and chlorine having the same shielding, as well as potassium and bromine. However, if we were to compare lithium to sodium, the shielding effect would be different for these 2 atoms because of the size or the number of energy levels occupied by electrons. Shielding can be described as barriers that are created by the core level electrons. The core level electrons would be the lower energy level electrons. When looking at lithium, we can see there is 1 energy level below the valence level, or the outermost level. However, when looking at sodium, we can see that there are 2 energy levels below the valence level. Likewise, looking at potassium, there are 3 energy levels below the valence level. We would therefore state that potassium has the greatest levels of shielding, or the greatest effect from shielding, when comparing lithium, sodium, and potassium. Looking back at the periodic table once again, lithium, sodium, and potassium, we see they're found in the same group. However, the period number 2, period number 3, period number 4, help us understand the effects of shielding. The greater the period number, the greater the effect from shielding upon an atom. This simply means when there are more energy levels, there are more core electrons shielding the valence electrons from the nucleus. When comparing fluorine, chlorine, and bromine, we can see there is one level of shielding for fluorine, two levels of shielding for chlorine, and three levels of shielding for bromine. Therefore, bromine has the greatest effect from shielding. Let us compare elements, however, that are found or located in the same period. By this, we can look at the elements of lithium compared to fluorine. Notice each of these are found in period 2 on the periodic table. When drawing models of these atoms, both lithium and fluorine would each have two energy levels occupied by electrons. They would also each have one level of shielding. Therefore, we say that they have the same effect from shielding. Likewise, the elements sodium and chlorine are also found in the same period, found in period 3. Therefore, sodium and chlorine would each have three energy levels occupied by electrons. You can see the Bohr models clearly illustrate this. This also means that each of these atoms would have two core levels or shielding levels of electrons. Therefore, we say they have the same effect from shielding. The same pattern holds true for potassium and bromine, which are also found in the same period on the periodic table, period number 4. This would require 4 energy levels occupied by electrons for each of these two atoms. Therefore, they would also have the same shielding effect, 3 levels of core electrons acting as shields. The shielding effect is similar to a barrier. It's created by the core level electrons. What it does is it weakens the attraction for valence electrons from the nucleus. If we were to draw a simple line segment from the nucleus outward to the valence electrons, we can actually see how the distance changes as energy levels or rings are added. Let us look at this for the elements of concern, lithium compared to sodium, as well as potassium. We can see if we draw a simple line segment from the nucleus to the outer region or the outer valence level, the distance gets greater as we move down the group, comparing lithium to sodium to potassium. This greater distance has an effect on the attraction for valence electrons. The greater the distance, the weaker the attraction would be for the valence electrons. Recall that electrons have a negative charge and the nucleus has a positive charge. There would therefore be a natural attraction between opposite charges. However, as that distance increases between the two particles, the attraction weakens, similar to having two magnets closer and drawing them further away. As you draw them further away, there's a weaker attractive force that would be felt between the two magnets. We can see the same pattern when we compare the fluorine, chlorine, and bromine atoms. By drawing a simple line segment from the nucleus outward, the distance of the line segment increases as we move down the group. Again, this weakens the attraction for valence electrons to the nucleus. This weaker attraction affects the behavior of atoms. Some atoms like to lose their valence electrons to become more stable, while others might want to attract them. This loss or attraction is affected by this distance from the nucleus or this attractive force created partly to shielding effect. Shielding effect works together with something known as nuclear charge. To simplify, nuclear charge might be thought of as the attractive force created by the proton count found in the nucleus of each atom. By comparing lithium to the element known as fluorine, we noticed before they have the same amount of shielding, or one level of shield. However, fluorine has additional protons in its nucleus. These additional protons create a stronger attractive force for the valence electrons. That stronger attractive force actually draws the atom's valence level in closer to the nucleus. Therefore, we get a shorter line segment from the nucleus to the outer region known as the valence level for fluorine than we would for lithium. Again, attractive force is one of the things that affects the behavior for valence electrons in atoms. The same pattern would hold true if we were to compare sodium to chlorine. Since they are found in the same period, they would each have 2 core levels of electrons, or the same effect from shielding. However, noticing when we look at the nucleus, chlorine has 17 protons, or a greater nuclear charge. Once again, this strengthens the attraction for valence electrons to the nucleus, related to the distance. The stronger attraction for the valence electrons created by a greater nuclear charge on chlorine actually makes a chlorine atom somewhat smaller than a sodium atom. This same pattern holds true when we compare potassium to bromine. Each of them would have 4 total energy levels, or 3 core levels of core electrons. 3 core levels of electrons would create the same effect for shielding for both potassium and bromine. However, bromine, having 35 protons in the nucleus, has a greater nuclear charge, causing the attraction from the nucleus to the valence level, or the outer ring of electrons, to be stronger than it would for potassium. We can see that shielding effect and nuclear charge work together. What they affect is the attraction for valence electrons. This attraction for valence electrons can reveal patterns that describe some of the behavior of chemical elements found on the periodic table. One of the patterns we can look at is something known as atomic radius. Atomic radius can just be thought of as the distance from the center of the nucleus to the outermost region known as the valence level, or the valence electrons. This distance is affected by 2 ideas: shielding effect and nuclear charge. The greater the number of shields, the larger atoms tend to be. The lesser number of shields, the smaller atoms tend to be. However, the attractive force from the number of protons in the nucleus can also affect the size of the atom. More protons tend to be thought of as a stronger magnetic attraction, therefore affecting the size of atoms. Let's apply this atomic radius idea by looking at the periodic table. When looking at the periodic table, we can see how the number of energy levels increases as we move down a group. Although we are circling the period numbers here, we're thinking about elements located in the same group, such as what is circled in purple. Hydrogen would have only 1 ring, or 1 energy level of electrons. However, lithium would need 2, sodium would need 3, potassium would need 4. As we continue to add rings, or energy levels, the radius, or the size of atoms, increases, moving downward on the periodic table. However, if we compare atoms that are found in the same period, when they're found in the same period, we take a look at the idea that they would each have what we would know as 2 energy levels, or 2 rings. Therefore, each of these atoms that are circled in green would have the same effect from shielding, but as we move across, the nuclear charge would increase. 5 protons, 6 protons, 7 protons, 8 protons. As the number of protons increases, the attractive force from the nucleus actually draws the valence electrons in closer, causing smaller atoms to be created as we move across from left to right. This would explain why lithium atoms are somewhat larger than fluorine atoms. It's because of the same effect from shielding, but additional nuclear charge found in the fluorine atom, 6 protons in fluorine versus 3. The additional protons create greater attractive force, drawing the valence level, or outer region, in closer to the nucleus, creating a smaller atomic radius. Shielding effect and nuclear charge also affect a concept or an idea known as ionization energy. Ionization energy might be thought of as the energy needed to remove an electron from an atom, creating what is known as an ion. In order to remove an electron from an atom, it must overcome the attraction from the nucleus. Therefore, when the distance from the nucleus to the outermost electron is a very great distance, that attraction is rather weak. This would describe why atoms like potassium have lower ionization energy than atoms like lithium or sodium. The distance from the nucleus to the outermost region, or valence electron, for potassium is a greater distance than it would be for sodium and lithium atoms. Therefore, when moving down any particular group in the periodic table, the ionization energy tends to get lower, requiring less energy to remove atoms because of the size. Once again, the size affects what we know as the attractive force for the valence electrons. Moving in the opposite direction from left to right, ionization energy actually begins to increase. This is because the atoms begin to get smaller when we move in this direction. Smaller atoms create stronger valence electron attraction, requiring more energy to remove them, or higher ionization energy. Shielding and nuclear charge also affect another concept known as electronegativity, which might be thought of as the ability to attract valence electrons into chemical bonds. This ability to attract is affected once again by the size of atoms created due to the shielding effect and nuclear charge. Recall that nonmetal elements tend to attract valence electrons to form chemical bonds. Let us compare the nonmetal elements of fluorine, chlorine, and bromine. Let's first look at the distance from the nucleus to the outermost level called the valence electrons. We can see this distance for bromine is the greatest distance, which means there would be the weakest attraction from the nucleus to the outermost energy level. We would therefore think that the electronegativity for bromine would be less than it would for chlorine and for fluorine. This distance is affected by the concepts of shielding and nuclear charge. Therefore, the ability to attract valence electrons into a bond would be greatest for fluorine, followed by chlorine, finally by bromine. We may sometimes exclude the ideas of comparing metals for electronegativity because their ability to attract valence electrons is not very much the pattern that we would look for. We would look for the loss of valence electrons for metallic elements. There's one final concept we need to look at, known as electron affinity, affected by shielding effect and nuclear charge. This might be thought of as the change in energy when a valence electron is gained. The pattern for electron affinity is identical to what we would see for electronegativity. While there may be exceptions, these patterns that we're talking about are general rules or patterns. Let us compare chlorine to bromine in this particular case. Since there is a stronger attraction for the valence electrons on what we know as chlorine atoms, that stronger attraction creates a greater release for energy when a valence electron is gained. As the attraction weakens for bromine, this would create a lower amount of electron affinity or less energy released when a valence electron is gained. Remembering these simple patterns or these trends can sometimes be difficult or a challenge. There is a lesson that will describe a simple method for trying to remember the trends or patterns related to the ideas that we spoke about in this lesson. It may be a good idea to view that lesson to help you with remembering. In summary, we took a look at the ideas of what shielding effect and nuclear charge are, as well as how they affect ideas like the atomic radius of atoms, the electron affinity of atoms, the electronegativity, or the ionization energy. It may be advised to try to memorize the definitions of those four terms: ionization energy, electronegativity, electron affinity, as well as atomic radius.